Okay, welcome everyone who is in person, on Zoom, watching later on YouTube to our Srad projects PDR 2021 to 2022. Very excited about the Srad projects we've been working on over the last year, basically, and specifically this semester. Here's how it's gonna go. First, we're gonna introduce the team, just like we did yesterday. Then we're gonna be talking a little bit about the EU. We switched up the order of these. So the oxidizer injection system will be going last. So the way we're going to do this too is we're going to go over all the slides, explain everything we have, and then at the very end, we'll have the questions. So if you have any questions, just save them for later. So now, I'm going to introduce myself too. My name is Herman Soriano, the project manager 2021-2022, and I'm really excited to show you what we have today.
Good afternoon, everybody. My name is Gustavo Santana. I am the Chief Engineer for Space City Rocketry for 2021-2020. I'm a Senior Mechanical Engineer, and I think we've done great work so far, and I'm happy and thank you guys. So a little bit about Space City Rocketry. We are one of two competition teams under AIAA at UH, and this year, I think we've been bigger than ever. Right now, we have roughly 80 members on the team. We've added semester, so it's a huge leap for us. The team is mostly undergrad students, so we do have some graduate students we rely on and enjoy their help with our projects, but we are mostly undergraduates. Our a lot of colleges, so the Cullen College of Engineering, the College of Technology, NSM, we have members. This year, I think we're more ambitious than ever. This is the first time that we want to compete in the 30K COTS category, a big leap for us. We're building a rocket from scratch for the first time in 3 years. So we also have some secondary missions that we want to get or we want to tackle while we're achieving those primary missions. And first and foremost, we want to begin development of a student research and develop projects. So as I was saying, the hybrid motor is one of them. The avionics has a ground station that they're working on. There's also the COTS propulsion team that are going to be working on a test stand. We also want to incentivize all our members to get L1s. The competition does require, since this year it's going to be held under EEE rules, they do require that any member that goes and does launch activities does have their L1 certificate. So we will be pushing that, and I think there's a lot of benefits that come with it. We also want to improve our technical writing and documentation for competition, as well as build team community and communication.
Okay, so let's talk a little bit about the team structure this year. We made a couple of changes from last year. We now have 6 sub-teams. At the very top, though, we do have AIAA-UH. We have our advisor, Randy. We have our faculty advisor, Dr. Siscon, and then JP Fuentes as our program manager. And of course, you have me as your project manager, and Gustavo as your chief engineer. So a couple of the changes we made this year compared to last year was that we did a rebranding of the analysis sub-team. They were working with electronic sensors last year, but we have moved all their work now to just avionics. So everything they worked in the past few years, now they're taking care of that. Anything electronics is now under avionics. And now what the new analysis sub-team focuses on is validation, testing, and simulations. So if you watch the Zenith PDR, you can see a lot of the work that they've been doing. Eventually, though, they will be working with the Srad project teams. And then the other big addition, which will be a heavy focus today, would be the Srad propulsion team. They are working with the capstone team that's developing an oxidizer injection system. So a lot of their work has been helping the team out and learning from them. And then this is the team demographics. We've done a lot of recruiting. We had a recruiting process again this year. We went into classes, recruited new members, different majors. Here's some of the information. So for the Srad PDR goals, we want to present all the progress we made this year with the Srad projects. We're going to discuss budget and maybe a little bit of the timeline for the sub teams, and hopefully get feedback from everyone who's attending today. So the project status right now for the Srad sub-teams, avionics, because of the work that was done by analysis over the last 2 years, or the old analysis sub-team. A lot of the research has already been completed. For propulsion though, we have started the idea of just making a brand new solid propellant test stand. I know we had an old one made by a previous capstone team. However, we do not feel like that it was good enough. So we want to, if we have the funding and if we can continue work, make our own. And then with the engineering capstone team, they're almost done. So 75% of their work has been completed. Now, let's talk a little bit about budget. So on the top right there, you're seeing the spending for Zenith. That is our #1 priority this year, is to get the funding for Zenith. It is a brand new rocket, so it is expensive. And you can look at there how much we're spending for each single sub team. And our current funding right now is $4,602. And what we need to fund Zenith, this doesn't include the Srad projects, is $5,306. There might be some things changing as we still have to redesign and continue some research with Zenith. But the other funding that we do need to, just because we want to keep pushing the Srad projects, is the at the bottom right there. That is just an estimate, at least for the solid propelled test stand. And then Srad avionics and the hybrid engine. For this year, we would like to have at least $2,200. So, of course, for planning, how are we going to get this money? Donations are the biggest thing. If we can get donations so we can be able to collect all this money and be able to pay off and compete in spaceport later this year, it will be greatly appreciated. Events, bake sales, and more sponsorships. We're going to be working really hard with the IAA and everyone else on the team to be able to fund this money and fund these projects. And now for the Srad timeline. So due to our priority right now being the completion of Zenith, there is not that many deadlines or any timeline for the Srad projects, but we do plan on December 11th to meet with all the Srad project leads to discuss a timeline, budget, and any milestones we have for the next semester. We'll have a better idea what our budget will be at the time, and we'll start working from there. But right now, let's talk a little bit about a project we started this year. This is very early development right now, so this is just a little bit of research we've done. So Tala, our sub-team lead for cloud propulsion, will come up right now. Thank you.
All right, so as far as our goals and objectives for the new solid propellant test stand, we do want to test motors up to potentially right now, we are thinking of up to a K-class motor. So we mainly want to create this new test stand just to advance our current data collecting abilities. So one of our big goals is to be able to produce experimental thrust curves and produce that ourselves, in addition to getting heat flux data, because right now SCR does not collect any heat data, and that has been something that has been asked, especially by some capstone teams. So this hopefully should fill that gap in our ability to collect data. So to satisfy these objectives, we split COTS propulsion into 3 different groups, so little subgroups. We have configuration materials and electronics to lay out the design of our new test stand. And a little bit more about our testing objectives. We are thinking of doing just testing single grain, though dual grain has been considered as well. One of our other objectives is to test how different grain geometries might alter the type of thrust curve we do get, or the shape of the thrust curve. So looking at that thrust time profile. We have been 2 of potentially the different geometries that we will be looking at include of course the Bates one, and just playing around with the different star or multiple fin geometries. And then so our first group was materials, and the candidate materials that we looked at, we did look at aluminum and two aluminum alloys right there, as well as stainless steel. We do have titanium on there, part of our decision matrix, just for the sake of completion and just a relative marker as far as how aluminum and stainless steel will measure up to it. When we do go to the decision matrix on the next slide, the titanium is just there, not as a true contender, but as a relative check. So this is the decision matrix right now as far as materials. Over here, we do see that stainless steel is leading the options. even though it is relatively close to aluminum. And the previous iteration of our test stand, the capstone test stand, is made out of aluminum. Mainly, I think the main difference right here would be a little bit about thermal properties. It did score a little bit better right here. But as far as cost, it is relatively the same. And as I mentioned previously, titanium is just there as a relative check. And as far as configuration went, we did consider so the two types of vertical, thrust pointing up or down, as well as horizontal. We do think that doing it vertical thrust pointing down would be the safest and makes the most sense. Mainly because if something were to go wrong, at least we mitigate just having a risk of just projectile shards. And so it would implant the motor into the ground if anything, if the structure were to fail. Though this configuration, we do admit that there are some drawbacks, mainly that it is an inaccurate representation of the flight because you have gravity and thrust going in the same direction. So something we do have to account for is that the weight will change during, or the weight changes during the burning fuel will not be considered sufficiently with this current configuration. And as mentioned, even though we do think vertical thrust pointing down is better, this is just a brief summary of how, when we consider the other two options. For horizontal, mainly, it is better, or it's most commonly seen when we do have liquid or hybrid motors. Since we are testing solid propellant here, it would not, we don't think it would be the best options right here. And as far as vertical thrust pointed up, it would be the most accurate representation of flight, but the safety factor or the safety considerations are going to be the trickiest, and we thought that we could get rid of that by choosing vertical thrust point down. And then as far as electronics, we will be using, as far as load cell, we will be using the one that we currently have in the lab, which is our 500-pound S-beam load cell. So this mainly it works for two reasons. For up to K class, that should be enough, as well as just budget-wise, it would be good to use equipment that we already have. And then, so these are different parts of the electronics as shown on the wiring diagram right here. So this is also one that we have left over from the capstone testing. It's rolling over to this one. Though some of the things that we are looking to change include that the old one uses an Arduino Mega, and we might be swapping out for a TC. And as far as the electronic housing unit, we were thinking of having just a single unit with all the electronics and the wiring included, mounting it onto one of the rail frames. So this is also up in the air right now. We are thinking of having it somewhere along the lower rail frame. But again, position has not been finalized. We were thinking of having something that, well, we know for sure has different slots for wires and something that we can take apart and put back together relatively quickly. So the current design looks something like this. From the wiring diagram that we did see on the previous slides, we would have our LCD screen right here pointed out, and these two sections do slot in and out, having the rail frame right here, and then these are removed for easier access. And that was it for the solid propellant test.
Right. So avionics is split up for Srad primarily into 4 different sections. You'll kind of see these as we go through the slides. Just kind of called out to them in the beginning. Our 4 different sections that we have kind of areas of focus would be a flight computer, a ground station, an Srad sensors team, just to kind of focus on what kind of sensors might be useful to further develop the rocket, as well as a telemetry team. So here's kind of a brief overview of the Srad sensors. Basically, the idea to them is we'll be applying sensors throughout the rocket to be able to determine areas to collect real-world data from that might allow us to further develop our rockets. A few examples of these will happen kind of as we go through here, but ultimately, the goal with this team is to be able to further the development of rockets by having real-world data that we've collected to be able to determine our materials and strength of things as we kind of move forward. So one of the sensors that we kind of talked about, it was a thermal gradient for the propulsion steam. You can see on the right there, there's a little bit of kind of math that has been looked into for the thermal gradient. One of the first things that we had to look at was thermocouplers versus thermistors. Thermistors obviously collect data quite a bit faster than thermocouplers, but thermocouplers allow us to work with a lot higher temperatures, and we assume that the motors are going to be under fairly high temperatures, somewhere around 500 Celsius. So we decided to go with thermocouplers instead of thermistors. While they do collect slower data, we're hoping that, at least it'll be good enough for our purposes, and not too much of a high cost. Obviously, budget is a huge concern. You can find thermistors that will work at very high temperatures, but for way too much. Currently, we're thinking of using 3 thermistors, thermocouplers across the motor tube, just to kind of have a basic understanding and a basic concept of what we can do with this, and hopefully expand that as years go on. And yeah, we're going to have a trade study done a little bit after the PDR. We want to make sure that we had, enough time to properly look through all our options and decide what would make the most sense as far as thermocouplers go. So it is something that had to be pushed beyond the PDR. One of the other ones that we talked about for structures would be strain gauges. Obviously, we want to have strain gauges on the fins, to be able to read the real world forces that'll happen on the fins as we're under launch. Some of the major things that we want to do is we want to try for 2 per fin, which will be costly. For now, we want to stick to 1 per fin, but the ultimate goal would be 2 per fin. And we want to have them read in 2 directions, which is a really important thing. So we want to have both the downwards force, so we can see, how the actual forces of pushing down on the rocket are as we launch, the drag forces, as well as how much the fins are flexing during flight, if there's any flex whatsoever. And that'll kind of give us some real world data that we can work with and hopefully pass off to the analysis team to be able to do some more information with. Again, with this, we have a trade study underway. Our criteria has kind of been highlighted under vibration durability, high accuracy, force safety factor, and cost. We had bought in some strain gauges before off of Amazon, and they were very cheap and they did not work out very well. So this criteria was kind of determined based off of that. Hopefully, these will start to be a little bit better. And you can see a picture of strain gauges on the right, as well as kind of some information that we have about them. So next we have the flight computers. So obviously the flight computer is the part of the rocket, part of the avionics, that deals with denoting the state of the rocket and applying useful information or denote the state of the rocket and applying appropriate actions. So you can see some of our sensors here, and we'll talk about each of those individually. So some of the objectives that we had for our flight computer: we want to be able to measure the atmospheric pressure, we want to measure acceleration, we want to be able to trigger parachute deployments. This is a little bit tentative, obviously, for SRAD. When we start off, we're not going to be able to trigger parachute deployments right off the bat. So it will be something that's a long-term goal once we have a lot of testing down to ensure that we're actually able to read and properly denote our states, which is a very important thing. Obtain gyroscopic readings, GPS tracking, logged flight data onto an SD card, and transmit real-time data to the ground station, as well as receive commands from the ground station. And we'll talk about all these a little bit more. So flight computer, predominantly for our main controller, we want to use the Teensy 4.1. The 4.1 is optimized for I/O. So it's out of all the Teensies, the architecture kind of changes as the numbers go up. And the 4 architecture is really designed around being able to read in and out really quickly information. And then it's kind of coupled with, the 4.1 has quite a few of I/O pins, so we found to be the best for us. For our barometer, we have a BMP 390. This was last year. We had a list of options that we were able to use for our barometers that was given to us by our chief engineer. And we conducted a trade study, and we believe this one to be the best option of that. So that's how we came to this one. Relative accuracy of about 3 pascals. We originally wanted to use I2C communication, but it's seeming like that might be a little bit too slow. So we're considering moving over to SBI. It's a built-in 3.3 volt regulator, and there's low altitude noise, and then we have our accelerometer gyroscope, which is the LSM6 SDSOX, which is a whole mouthful. You can see it's a fairly low power consumption, which is something that's really important to us, as we'll be running off a 9-volt battery. We want to make sure that we have optimal time, potentially 3.3 volt, 3.7 volt that we've been looking at. This one also uses either SPI or I2C. It has an analog voltage supply of around 1.7 volts to 3.6 volts. It's able to read fairly well in our kind of tilts for acceleration, for gyroscopic data. Maximum acceleration works to about 34 gravities, and the standard data sampling rate is from 1.6 hertz to 6.7 kilohertz. Dimensions are there. So then we have the GPS breakout board. This one is going to be important for us to be able to get the last known location of the rocket, obviously. And this will just kind of give us, like to be able to have a live read so we can find our rocket a lot easier when it's on the ground. And you can see some information about it there. We have the XP here, which is kind of a little bit under our telemetry, but it will also go on the flight computer. You'll notice that all these parts are kind of all linked together to each other, so they kind of have some overlap. So the XP is our way of communicating via ham radio back over to the ground station that we will be hoping to develop this year. And that'll just kind of allow us to get some like live read of the information and be able to control the rocket, do grounds testings, things like that, just to ensure that everything is working correctly. You can see there's a receiving and transmitting on there, power draws. And you can see range is up to about 9 miles with a dipole antenna and 28 miles with a Yagi antenna. And the frequency ranges are listed on there. So next we have the ground station. So the ground station will be allow us to kind of view our information live as we're actually launching. The most useful information that we're hoping to get on here is the maximum altitude of our rocket. That way we can know, what our apogee was very easily, as well as the last known location of the rocket. Obviously, currently we have a COTS ground station that involves us carrying a laptop and a big antenna out in the middle of a field. And ideally, this station will be a lot slimmer and a lot smaller, so that way we don't have to carry out a laptop and this huge antenna, but instead this little small box in which it's all built into. And we'll have, a nice, easy to read screen because LCDs can be kind of hard to see in the sunlight. But a little bit more about that. Here's the connection types trade study. So we talked about how we're going to hook up the XP to which device that we want to use. So our options were we can hook it up to a Teensy, which is like a souped up Arduino for those of you who are unfamiliar. We could do the XP to a Raspberry Pi. And we could also do an XP to a Teensy to a Pi. And ultimately, we found that an XP to a Pi would be our best option because the Pi allows us to have the most kind of expandability. XP to a Teensy to a Pi would allow us to, reuse that code that we're using for the XP to send data almost exactly to receive, but then, processing it again in a Pi seemed like a little bit of an extra step. And the Teensy by itself, XP to Teensy, is functionally cool, but ultimately we don't get as much power as we would with the Raspberry Pi. So we felt that that was not the option that we wanted to go with. Here you can see a little bit of how we're connecting things, as well as some specs about the Raspberry Pi. We're currently thinking of using the Raspberry Pi B4. I believe in here, I believe in our bill of materials, we had selected a 2 GB model. Upon further inspection and kind of talking with the team, I think that we'll be having quite a bit of code running on here, and we might opt to upgrade to an 8 GB model. We will double check that and make sure that it's something that we would need, but it's looking like it is very likely. Otherwise, we have a display port for a 7-inch screen, which is something that will be talked about a little bit later as well. USB ports, micro HDMI ports, and a 5-volt connection. So it's nice and easy to power. Here's an OLED trade study. So if you guys recall, I mentioned I wanted to have an OLED screen, so it's nice and easy to read in the sunlight. Obviously, reading off of a laptop is, same thing if you're looking at your phone, functionally very hard and not very practical. OLEDs tend to be a lot easier to see in sunlight, and especially we want to go with the black and white OLED, so the contrast is really high, so it's nice and easy. And this will allow us to much easier get our data and kind of be able to find the location and plug things into our phone, GPS coordinates and whatnot that we might need. And you can see here we started with 3 different options from Adafruit, and we ended up liking the 128 by 64 OLED that was built for the Raspberry Pi. Ideally, obviously, all of these would work on the Raspberry Pi. So we looked at afterwards, but it seems to be the one in the middle there I like the most. So here's actually that OLED screen that we talked about. So it's Raspberry Pi supported. Here's the dimensions, the weights. It has the Joy-Cons on the sides, which is going to be pretty cool. We're hoping that we can use that to kind of switch between altitude and GPS location, and potentially other information should we add to the ground station later on. Just gives us a nice way to kind of, hit the little arrow to move to the side and see a different screen, or, scroll over if we need to see more for our coordinates, if we're getting more coordinates that we can put on the screen. And obviously monochrome black and white was an important thing. First of all, that brings down the price of this, as well as makes it easier to read in the sunlight, which is 2 things that we wanted to make sure that we had high focus on. Here are some optional features trade study. So at the beginning of the year, we kind of had a talk with all of avionics, and I was like, hey, here is the what we want to do this year. Is there any features that you guys would like to add in that I've potentially not thought about? Kind because I kept it kind of to the this we need functionally to be a ground station. You know, we have to have working way of having data sent back to us or reading it off the flight computer. And these are some features that they wanted to add in that was, you know, not necessarily required, but they thought would be a really cool thing to have. You can see a 7-inch portable screen. They wanted to add a 3D render of the rocket. Obviously, this is not a priority of ours, but this is something that we want to add in on there. So that way we can have kind of from our gyroscopic data, be able to create a 3D render locally. So you can just kind of see how the rocket is oriented in 3D space, as well as an LED colors to showcase expected release. So if you guys recall, for the flight computer, we can't actually hook it up to any form of black powder or anything like that, because functionally, until we've gotten a lot of testing under our belt, we don't know that there's some random edge case that we cannot account for. So these lights would be able to kind of denote for us when the flight computer believes it's reached apogee, it can send over a code to the ground station in order to turn on an LED. And that way we can indicate where we expected apogee to be, as well as we expected main to be, and compare that to our actual data that we have collected on our like working flight computers that we know will functionally work. And that way you can test for random edge cases that we may not have considered before. So here is that screen that we talked about for the 3D model. So it is Raspberry Pi supported. The dimensions are on there. It is a 480 screen. It doesn't need to be, you know, too high quality. We're just going to do some quick rendering on there. It is touchscreen. So if we want to add in some potential control features later on, maybe remote e-match firing, things like that, we have that ability kind of built in here into the display as it is touchscreen. It is LCD. We don't have too big of a priority on too much visibility here. It would be cool again, and it's one of those that you kind of expected not to be, you know, walking around in the middle of a field in Mexico while actively looking at this. It would be during the launch time, so you'd actually be able to have a little more visibility versus the OLED screen you'd actually be actively looking at while you're walking around the field. So I would expect, you know, a little bit harder visibility there. Here are some of the LED pins that we talked about earlier. So we were looking at 3.5 millimeter LEDs. Those are your standard LEDs that you get with almost any like beginner electronics kit. Obviously through hole, no SMD. It'll showcase 6 different states of the rocket, which you can see on there. So we have boost, fast, coast, drogue, main, and landed. I believe we're actually missing a pad, but I guess, excuse me. We actually talked about that earlier. We don't want to do pad just because, you know, we don't really need a denoted state for that. That should be kind of inherent. So boost, fast, coast, drogue, and main, landed all came from our COT system. So boost is obviously while the motor is being actively burned. Fast is during that initial state where it has a high momentum, but the motor is not being burned. Coast is kind of that pickup as we are losing a lot of that speed. Drogue is the main release of it, or the drogue release, excuse me. And then main is obviously the main release, and then landed is what's on the ground. And hopefully we're hoping to be able to note each of these states so that we can kind of further develop our flight computer. Obviously, having boost, fast, and coast is not completely necessary, but it allows us to kind of know that our reads are as accurate as we can get. And that way, you know, if we have any errors with our drogue or our main, we can kind of look back at that data and see like, hey, you know, that started beforehand or afterhand. Yes. So future plans, some of the things that we want to have going forward, we want to have a way of setting off the black powder charges. So we want to have something that is a physical switch that you have to press and hold. So for those of you guys who are familiar with our current ground station, there is a button that you have to press to set off the e-matches, and you have a 10-second countdown during that time in which you have to press another button in order to actually fire it. So that way you don't accidentally click a button and blow up someone's hand. Same thing here. We want to have some way that you have to physically turn something on that can be electrically connected and disconnected, as well as a software means of once that thing is physically connected, then you can go in and actually fire it. We're going to safely and remotely turn off the avionics system. This is definitely a long-term goal for us. One idea that we want to try and get, ultimately, is the means of being able to disconnect the electronic system for avionics. That has to be a physical disconnect as per AAA rules, but we want to do it entirely remotely. So currently the way that we have to do it, not entirely remotely, but from outside of the rocket. Currently the way that we have to do it is we have to be inside of the rocket physically, you know, with the screwdriver and, you know, turn on our screw switches. We want to try and find a way in which we can turn it on from outside of the rocket, ideally on our ground station. And obviously we want to be able to transmit the rocket's GPS coordinates, temperatures, voltage, and other useful information over ham radio bands and be able to display them on our ground station. Here is a kind of risk matrix that we have kind of very briefly built. Obviously, a lot of this has not been, physically developed yet, as we're kind of in the research stage for a lot of this right now. And we need more parts to kind of move forward. But this is kind of what we've come up with right now. So unknown GPS coordinates, probably since we're beginning, will be a very more often than we would expect. So we put it under occasional. And if it does happen, obviously it's not our main flight computer. It's not our main source of getting it. So hopefully it's not going to be too bad, but we did put it under critical just in case we can't see it, or in case we lose, from here might mean we're losing from our main flight computer as well. Seldom and catastrophic, we have uploading the wrong file. So if we upload the wrong firmware or the wrong code onto there, obviously that is a potential issue. Very unlikely we would plan to have the code finalized and tested before we put it up on anything, but if it does happen, it can be pretty bad. Obviously our main goal is being able to collect this information. So if we can't collect any information, that would be very bad. Improbable and catastrophic is damage from V dropping it. One of my sub team members did that. Yes. Telemetry overview. So telemetry is another one of our systems that we have on here. And obviously telemetry, we want to optimize kind of the way that we can send data over telemetry and radio waves from our flight computer to our ground station. So we have an entire team kind of dedicated to optimization and being able to compress this data as much as possible. So that way we can send over as much information over the waves as we can, using as little power as we need to. And ideally, as short antennas as we have to, that are still going to be feasibly workable. Especially at 30,000 feet, which ultimately we won't be flying with there first, but for the long-term goals. Today it will be collected somewhere around 100 hertz, and we want to send over data at least at 1 hertz, ideally somewhere closer to 10 hertz. Obviously, these will be done over the XB, as we talked about a little bit earlier in the flight computer and the ground station. So there will be XBs, both receiver and transceiver, one on the flight computer and the other one on the ground station. We want to use a directional Yagi antenna that's kind of going to be built into our ground station that we can kind of read from there, and that'll be attached directly to the XB. And then live information will ideally be displayed from the ground station on the ground station from the flight computer, and be stored also on the flight computer in an SD card for kind of readout afterwards. So we have telemetry, ham radio, and ASRP packet control protocol. Excuse me. There's quite a bit of stuff on here. I think I'm going a little bit too far here. You guys are welcome to read over this. There's quite a bit of useful information, but just to kind of speed things up, because I've taken a lot of time. We have here our bill of materials. As you can see, we're around $800. A lot of the stuff that we needed, we tried to repurpose from lab or find cheaper options for. And ultimately, you can see there's quite a few zeros just because we're repurposing stuff from lab. As well as Pratt series, we've kind of got it through Prometheus's electronics, as well as Oberon's, and just whatever we have. I know Emily offered us some stuff that was in her case in the back. So we still are needing in about $800 worth to ideally finish everything that we've talked about today. And yeah, I think that it should be it for me.
Hey guys, good afternoon. My name is Osvaldo Martinez, or Ozzy. Everyone knows me as Ozzy. I am this year's SRAD propulsion lead. It's a new sub-team that we have put in place to develop SRAD competition engines or motors for both the 10K Oberon flight and 30K Oberon/CNET flight. We have actually been working closely with the Capstone team, as many of you guys have already known. Most of the hybrid engine project has been brought to us by the Capstone team itself. We have been there to help them in completing the project as quickly as possible to meet that Capstone deadline, but also because they are laying the foundation for Space City rocketry, we're helping them to complete their capstone so that they can then provide us with the foundation for us to continue working on that project. So here's a small overview of SRAD propulsion. These are some of the projects we have on the side, aside from the help with the Capstone team. We have, of course, the solid rocket fuel. Most of this data had been collected last semester by some of the COTS propulsion members near the end of last year. I believe that COTS Propulsion is also working on this, and we'd love to work together, but mostly it's going to be an ammonium perchlorate composite propellant that we are planning to mix and mold in the lab. From there, we also have, we're looking forward to mixing those fuels and testing them in the lab, which is, single grain or dual grain 56 millimeter testing that will allow us to not only validate the propellant, but also the test stand. Either the last year's capstone team or the previous year capstone team and the new one that we're developing. Should be an awesome way to test out, basically take two birds, one stone. Also the modified test stand. We've also been working on that one to strengthen it up, get some of the connections and joints to be a lot stronger to withstand the amount of force required by some of these motors. Haven't completed any FEA or analysis on it. We're looking forward to partnering up with analysis to complete that, to see how strong it is, and using that information to create the new test stand with COTS Propulsion. So of course, one of the main advantages of having an SRAD propulsion sub-team is the fact that we can actually work with all of our other sub-teams in Space City Rocketry. Here's a small list of some of the joint projects that we have worked on. Really like to thank Avionics for helping out the capstone team and us as well for helping us develop helping them develop the valve control system, specifically speaking about the electronics and the microcontroller. Of course, thanks to COTS Propulsion for really helping us get through the modifications for the previous capstone test stand. They've been great help, and they've helped us out for the past 2 months. So it's been awesome. Data validation and testing. We've worked with Ravi already in analysis, but we're planning on working a lot more with them. So as they continue on their sub-team and their projects and get better with their analysis, we will then provide them with even more data to work together and really have a great foundation and great testing for all of these projects. And of course, haven't worked with them yet, but in the coming semesters, we're hoping to work with structures for the manufacturing and development of pressure vessels for the oxidizer, helium tanks, as well as mounting those tanks to the airframes. So a lot of projects that we can work with other sub-teams with. So I'm gonna introduce the capstone team for you guys. The capstone team there's 4 members in the capstone team. It's a mechanical engineering capstone team where they're working on a hybrid rocket engine, specifically the oxidizer injection system. They are Alejandro Martinez, Andrew Dougherty, Christian Emanis, and Oscar Mendez. They are actually the ones that provided all of this information for us. We had actually not had any time to complete any of the research involved with the hybrid motor engine. So we are relying 100% on them, but then they will pass this information down to us and continue the development. So their proposal, they propose that they will research and develop an oxidizer injection system capable of taking Space City Rocketry's competition rockets. At the time it was Oberon, but now it's looking like we could use Zenith, and meet a mass flow requirement of, 2.88 kilograms per second maximum to a theoretical 47,000 Newton second impulse. The reason that it's so high, I'll explain it in a later slide. Scope of work and fundamentals. Of course, the oxidizer injection system will include a lot of other systems for the engine, mainly oxidizer tank and a pressurizing pressurant helium tank to go along with it, the valve control system, minor sensors, igniters, and of course, the development of a hybrid solid fuel. All right, so main focus on the injection system. Of course, they've developed this themselves. They have done the mathematics and done some testing and theorizing for their project. And they have come to the conclusion that they will need around 17 kilograms of oxidizer to provide the necessary thrust or impulse for the rocket. So of course, here at the bottom is a couple of pictures of the injector plate and bell that have already been manufactured. Both of them have already been pressure tested to about 2,000 or exceeding 2,000 PSI, which is already twice as the amount of PSI required for operation. And on top is a test completed by another organization of how the injection system will look when ran with water at several pressures. We're at different pressures. Us, along with the capstone team, are looking to complete that testing before the end of the first week of December, so we can get some of those pictures on our own. All right, and of course, they did provide us with a couple of decision matrix that they thought that they have deemed viable. They have the geometry for the injector plate. They had several geometries: shower head, angled, axial, and vortex, and their factors and weights and totals according to those, as well as the material decision matrix for the materials of that hardware. All right, so flow control. It is very obvious that the majority of the effort into a hybrid motor system is the optimization of the flow of oxidizer into the combustion chamber. In order to reach the required 30K of altitude, along with the extra weight brought along with the hybrid engine, it is estimated, of course, again, that it would need about 17 kilograms of oxidizer, and it'll have to flow through that in about 9.5 seconds. The valve control system then is going to be very crucial for this hybrid motor. It is designed with multiple pressure transducers, as well as a main ball valve connected to an electronics microcontroller, and a flow rate sensor as well. So the pressure transducers will not only measure the pressure in the combustion chamber and the oxidizer tank, but also reference the flow rate sensor to ensure that everything's optimized correctly. Because of the optimization, it is crucial that we have a good oxidizer to fuel rate ratio. And at the top, you can see what different mass flux does to the fuel regression in the solid portion of the hybrid engine. Here's the weighted decision matrix for the oxidizer control valve. They have chosen to go with the ball valve and gear reduction, mainly due to time constraints and because they weren't able to get some of these components in time. But at the end, they have decided that they do want to do the solenoid valve as their main valve control. All right, so pressure vessels. Although the pressure vessels were not in the scope of work of the capstone team, they did complete some research into the pressure vessels. It is after the capstone team has completed their testing and for their capstone deadline, it is on the Space City Rocketry team and specifically Srad Propulsion to develop these pressure vessels. On the right, on the right, you see a couple of pictures of the idea of what we're thinking of doing for our pressure vessels using aluminum cylinders or stainless steel cylinders with aluminum bulkheads that will be bolted on to create that, to hold the oxidizer and the helium. Same thing goes for the combustion chamber. The injector bell and injector plate you see are actually just loose, but in the final product, there's going to be some modifications done to those, but they will be pushed into a basically the same idea that you see with the pressure vessels by bolting it on with O-rings to make sure it's a good seal. And here is they actually did provide this for us, the weighted table comparing the different materials for the pressure vessels. They did consider different types of aluminum, 6061, as well as a carbon fiber composite tank and titanium. The main disadvantages of composite and titanium, of course, being the cost and the manufacturability. So electronics and data, once again, them and Srad Propulsion thank Avionics for their help. They worked together to come up with a decision to use a TNC 4.1 to run the valve control system electronics. The controller will handle all types of data collection as well as the main valve control. The code for the controller, they're still working on that. It is supposed to read all the sensors, adjust the flow rate accordingly, according to the solid fuel regression, and keep readings of the combustion chamber pressure. Data collection is crucial, of course, because we are completing these tests and it's going to be a prototype hybrid rocket engine. We do have to capture as much data as we can in order to optimize the motor so that it can continue to perform efficiently and at the right pressures, and so that to make sure we're not exceeding any of the safety factors. And of course, the sensors, I did mention them. There is 2 pressure transducers, as well as a flow rate sensor and a motor with a main ball valve for the control. So of course, keep in mind that this project is a work in progress. Most of the components for the Capstone's hybrid rocket oxidizer injection system have been completed, as you can see in the picture on the right. That is the injector plate and bell, along with the valve and some fittings where when it was tested with water pressure. So since it is a work in progress, there's still a lot of work for us to complete. The Capstone team has basically laid a foundation for us to continue their research and continue developing this hybrid rocket engine. We will continue to develop this after their deadline, specifically with the other Space City Rocketry sub-teams. And if you guys want some insight on some of the things we have to tackle into the coming semesters, we do have to get with several sub-teams for the development of the tanks, the mounting mechanisms for the hybrid rocket engine, the valve and command center, so the fill station valves and command center, my bad, and also the engine electronics. So the tanks and the combustion chamber have to be connected together. Here is a bill of materials. This is a rough estimate. In here is also included some of the Srad solid propulsion stuff, mainly a bunch of different chemicals and tools required to mix fuels in the lab, as well as most of the hardware needed for pressure vessels or the valve control bay. That's it.
Just I guess a point with the testing, we do have in contact with the chemical safety department at UH, and we have planned, or we will plan a meeting with them to make sure everything we're doing is safe and to be done at the right location. Same with the storage of everything. We will have to talk with them to make sure everything is safe. All right, so some final points for today. I want to thank everyone who presented today and everyone's here. But as far as just Space City Rocketry, and I guess this concludes everything we presented for the last 2 days, Zenith and Srad are both ambitious. As Gustavo mentioned, this is the first time in 3 years we're building a rocket from scratch. And the Srad projects are a lot more complicated than whatever we've done for COTS. So there's still a lot of work that has to get done, specifically in the next month for Zenith. Yeah, it's going to be hard, but one thing that Gustavo and I are very sure of is that this is a time for us to pursue these projects and continue working on Zenith. We have more members than we ever had before. And even better, we have members who are very ambitious and are willing to work really hard. And we're really confident that everything we're planning on doing will be done because we know we can work hard and we have the people to do the work. Again, thank you everyone for this. And paying attention to the presentation. Now we're gonna move on to questions, but right before we move on to questions, again, we're gonna have a 5-minute break for use the restroom, everything. If there's any questions online, we have moderators here who are taking notes, and they'll be handling that. And when we come back, there will be questions. Thank you.
Right, so we're hoping to get our sensors running at around 100 hertz. That seems to be what our COT system, our telemetry V3, which is our like kind of primary and our better COT system is running at. So we're hoping to aim kind of around there in that kind of ballpark. Last year, the analysis team that was working with electronics, they went with I2C for their communications, and they were kind of getting lucky to hit around 40 hertz. So we're going to assume for the moment that I2C is not going to be fast enough for our purposes. And so we're going to go with SPI, but yeah, we're aiming for about 100 hertz. And then I think I can get to the next question real quick here. So the question asks, what is the operational concept for the ground station? Is it going to be a handheld device that a person can carry around in the field? What sort of data will be displayed on the screen? So the idea is, yes, it's going to be a handheld device. It's kind of going to be like a box shape, I would say is the easiest thing to consider, with an antenna sticking out of it. So currently our ground station is whoever's laptop is there, attached to a Yagi antenna over a huge cable thingy. Not the most convenient, it's an adapter, excuse me. Not the most convenient option to be able to read off of. The LCDs are hard to read. Carrying that around in New Mexico desert heat, crawling under fences is not something that we really want to do. So we want to optimize it to be in a small as possible kind of container that is nice and lightweight, that'll have our screens, whatever information on there. Ideally weigh less than a laptop, definitely take up less space than a laptop. And just something that, laptop with an antenna and everything, and just something that's easier to generally carry around. As for what sort of data will be displayed on the screen, the first screen that we're going to have as the OLED screen is going to ideally display our information about the highest altitude of the rocket. So that way we know what our apogee was. And then it will also display our last known GPS location. So whatever the last location you could ping on the rocket, give us that information so that we can find it easier. And again, the OLED screen is the one that's going to be nice and easy to read in the sunlight. And then the LCD screen, which is going to be a little bit harder to view in the sunlight, will display information that's not necessary for recovering the rocket. Information like potentially a 3D model of the rocket and its gyroscopic positioning. So that way we can kind of see, in 3D space, how is our rocket currently orientated, which is one of those things that is functionally cool, but not necessary for the recovery of the rocket. So it's going to be on a screen that does not necessarily have to be seen as well.
Great. I guess the timeline, as is said now, is the injection system is due to be tested with only either carbon dioxide or pressurized water by hopefully next month. But as far as the pressure vessels go, those are not even in the development stage yet. So we still have to come up with a 3D model and FEA for those 3D models. And the manufacturing probably won't start until after Zenith is completed. Most of the price for those pressure vessels comes from the raw materials themselves, and they do require a lot of manufacturing and machining. So it probably won't start till, good estimate, next semester. I'm sorry, next fall. So a little bit of time, but we just got a lot of time to test and model them up. But it should be good.
Any in-person questions?
All right, go ahead. Hit me with.
So at the very beginning, intro, I guess maybe you could use notes for y'all, but what does 70% done mean? What does 100% done mean? As for avionics, for prop, I saw the number 70%, 75% for capstone. I just want to know, like,
Sure.
what is 70%? What is 100%? What is a milestone you're trying to reach?
Do you want to answer mine?
Yeah, a general number, I don't know what that means.
So a lot of this stuff right now, specifically for SR Propulsion and everyone else, is up in the air based on the funding. So there is not a very good metric, but thank you for letting us know that that's something we really got to talk about and improve on. Specifically for the CDR next year or next semester, we'll have more information for them. And then,
I will say specifically for the hybrid capstone, that 75% includes all of the hardware purchased and machined or manufactured, all of the electronics assembled, coding being worked on. And the only thing that's left to do is just mount it all up, connect it and test it using the carbon dioxide and water pressures to do that test I showed you guys earlier. But that's what 75% is for hybrid capstone.
I think it's very important I saw like the general budgets, like how much money is needed to finish Zenith along with extra stuff for I know people like myself to provide what those, like similar to what avionics did, which is awesome. The bill of materials, exactly like what the hell you're trying to buy or need. But there's stuff like that, the plain leftover like garbage, like from like my job, that's like thrown away and scrapped in. But if I know they're looking for like scrap steel, scrap aluminum, like I can plug that out of the garbage and give it to you for free, and I'll take cut your cost out by half. Like, the thing is, I don't know how much you cut down because I don't know what that $1,000 is, or let's say profit. I don't know what that is. So maybe someone like me can give me the bill of materials, or you can at least have it handy so that I know that I have all that stuff around laying around. Because what is $1,000? So
Okay.
that's another note.
Yeah. They were on yesterday's slides for like the sub team. All the bill of materials for all the Zenith stuff was there, but I'll send you that specifically so you can take a look at yesterday's slides.
There's also a consolidated list for bill of materials and parts list for everything, and I can send you a link to that as well.
I mean, I keep going.
Keep going.
Yeah, go for it.
So the solid propellant test stand, I believe.
Mhm.
Yeah, that section. For luckily, I'm pretty knowledgeable of what the motor classes are, but what is K class compared to what Overon use or Zenith needs or other things, like how far along the motor class is that, and is that useful for what we need? Yeah, like, what does that K class mean in terms of impulse required? Heat data, why do we need that, and like, what are we learning from that? 'Cause I know it's on there, and I know why it's useful, but I'm not sure if y'all know why it's useful, and what you're trying to learn with that. And then you can answer those questions before.
As far as the heat data, that was something that the capstone NMM, I believe it was NMM, that, yes, they asked for specifically, and it was because we just have no heat data whatsoever. So I don't know if like we wanted to fill that gap. And so, I mean, I know you said that do we know why we need it? It was, let's just have it in case an NMM capsule comes along, saying that we just don't test for that. Doesn't make us look,
So,
You mind if I answer the impulse question?
Mhm.
Okay, so for the impulse of those test stands, the current sensor that we have is literally the only thing limiting us from testing larger motors. So the sensor we have, that Optima sensor, currently has a maximum load of 500 with a factor of safety of 150. So it could test up to 700, or yeah, somewhere around there, 700 pounds of force, which is around, I'd say 2,200 newtons of thrust, and that's peak thrust. Some of the motors that fall within that class is maximum an L class motor. I have seen some Optimus sensors that will reach a maximum load of about 1,500 pounds, which will allow us to test up to N class motors. So it's all a matter of the sensor, mainly the sensor, but also doing those FEI analysis for the materials and seeing what loads they can bear.
And to kind of go on about the heat data, I say that because actually Dom and I were the ones to be the ones first to say we were the first ones that can have a sub team, and we said let's put the chemicals on there. Why the hell not? And then we justified it with we wanted to try to make M out of plastic. We didn't know and the motor would get hot enough to melt plastic. That's kind of what we would, because like aluminum light is very heavy, 10% infill plastics. But I'm currently working on determining that. I also realize that combustion stability along the length of the motor is important. Not necessarily for COTS motors, because it's COTS, the best time for SRAD motors. If you have something burning really hot up there, really cold up there, something's kind of going whack in there. And we expect to heat that up. But somebody here is more knowledgeable than I am about that. And I do want to mention Ideally, it'd be really cool that you could do single grain test, because like big motors, scary. Boom. You don't want that, right? And at work, they're doing like a test stand, and you have to be like 1,000 feet away from it, just to even get close to it, because how the amount of energy stored in its tanks there. And it's really annoying to like work with. We haven't done it yet, but just the operational process of doing that's annoying. So if you do smaller things, especially because we haven't really, I'm not sure if you guys have done any solid rocket testing, like making your own grains, but making your first motor 500 pounds. It's kind of scary.
It's pretty heavy.
They should do like a 20-pound little whatever.
Yeah, that's what that little motor we had laying around. It's like a little 56 millimeter single or dual. Yeah, we had it laying around. I was like, why buy another one? We could just test one of those. I think it's fairly small.
Yeah.
So I think it should be good. And because it is a dual grain, it'll allow us to test specifically some of the mathematics behind it. Mainly, the port to throat ratios and some of the other like nozzle geometries. A lot of that goes down to how wide the inner diameter of the grain is, and also how long the actual grain is.
Yeah.
So it'd be great to use that little longer one to test some of those, to test some of that math.
And now for the solid propellant test stand, I saw that aluminum is one of the highest out of there. And I saw that yours is aluminum, stainless steel, and titanium. And what's not mentioned on there was regular carbon steel. Carbon steel is dirt cheap. It does rust, but you can do plenty of things that are, it's grinding and a model spray paint. And that is no more rust. You have to worry about that ever again. Which is like super cheap, and stainless steel is like usually, at least on fine stuff I've worked, much more expensive for carbon steel versus stainless steel. So that's something worth looking into. Prices on McMaster, I'm sure you guys have seen that. You can have a look at that. But I don't think you should rule out stainless. I mean, rule out regular carbon steel. Like I think it's called low carbon steel, whatever, McMaster. And also just I guess to help with the notes in general. You're talking about the location of something being the rail frame. I didn't really quite know what the proposed test stand would look like, so I don't know what the rail frame was.
Yeah, that was based on, so that was just like a ballpark based on like the capstone testing. So if it was going to be a similar shape, it would be on the board.
Okay.
But yeah, yes, it is a little bit abstract. So
Yeah,
I get it, yeah.
If we put like a little arrow, like on board or whatever, like rail frame area.
I think it was in the report that it's individual size, but yeah.
Okay. That's all I have for the solid propellant test stand.
So a lot of my questions will tie in with parents as well. So I sort of understand why you guys capped it at an A-class motor. But if the load cell is able to do an L-class, then why not just push your requirements to that? Because then you can cover a level 1 and level 2 set motors. And then later on, you can worry about attaching a bigger load cell for level 3 stuff that's going to be needed for where you have a big competition rocket. So it can be useful to design the test stand in such a way so that you start out small but have it be able to scale up to do like these large motors, especially in like 2 or 3 years time when the team might be looking to expert competition. And that's when you need to get that on the decision matrix, you have the thermal properties of each material. I'm just curious on how you think like the exhaust gas will actually affect the test in such a way that that becomes pretty significant material for you guys.
I think this was before we decided on a specific configuration and just in case, because I know we were considering it as like a horizontal potentially. I think this came first and that's why it was sorted this way. So we might have gone about it a little bit.
It's a good idea to think about all that, but if your motor burns for maximum 5 seconds and the frame isn't really in contact with the exhaust, then that thermal properties will point there. So you maybe score that a bit likely with the switch matrix. And that will also help with probably roller steel as well. As I said, it's the cheap, you can get it anywhere. And the only problem is the rust, but it can also help with making it easier to weld stuff instead of bolting together, make it generally stronger, and then just a thick coating to make sure. And I guess this whole team just likes teamsies.
Can I chime in on that one, actually?
Yeah, go for it.
Yeah,
I
so-
understand why. But I don't know.
Yeah, I figure you would, but just to answer that real quick. Obviously Arduinos are fully open source and they're really cool and they're really functional, but the TeamZ offers a lot more functionality and it's a lot more powerful. It's a little bit higher of a price point. It does have a proprietary bootloader, but ultimately, especially architecturally wise, they're very well optimized. Arduino has a lot of different branches, the Pro Nano, Micro, things like that, Uno, whatever. TeamZ is kind of has their focuses built on the version numbers, but each version of it is built to kind of focus on a different area. And for a lot of our work, we're working with IO, and we would like to have that power and that speed that comes with the TeamZ that's not quite the same on an Arduino. So yeah, just for anyone who's wondering why that is.
I know a ton of Adafruit sensors are compatible with Arduino and Raspberry Pis. Is it the same compatibility with teams as well?
Yes. So as my professor likes to say, C code will run on anything. You just have to compile it for that environment. So if you compile it for TeamZ, the sensors will run on TeamZ, and generally better than they do on Arduino.
Also, keep in mind that the valve control for the hybrid motor, that electronic was chosen as quickly as possible as per the requirements for the capstone team. So they really didn't have too much time to look into decision matrix. They just wanted to have something that was powerful, overpowered basically for what they needed, just so they can start working on it.
I need to throw a little bit more on there. It's a direct analog read from that pressure sensor that they're reading right there. So all you need is something that has a quick analog reader, and TeamZ was perfect for that.
That's all for
That's all for avionics.
Okay.
But I'm not sure. Yeah. So for the ground station for avionics, you plan on getting local information, like as a local environmental information.
That's not something that we're looking to collecting. If you mean like getting like like maybe humidity or something like that, that's not something that we're looking at collecting right now. Is that something you think we should consider? Oh, wind speeds is a good, yes.
That's why I certainly think, I remember, it stuck with me whenever I was in New Mexico. When we were there. I saw like, I forget what awesome team, like they set up a little weather station. They put up a pool, they had like the directional.
That's
thing
really
to see
cool.
which that a little anemometer.
Yeah, the rooster with an arrow.
They had a like the equivalent of like a big gun case thing that they opened up on a little stand, and they had all the readings of temperature, humidity, because all those things are put into your rock sim or whatever you open rocket, and you can drag it onto locally, not just going on your iPhone and doing like weather and then going that.
So I will say one thing that we wanted to do with our flight computer that we can also implement again into the ground station. This was kind of a long-term goal, and that's why we didn't have too much about it on here. But the way that we want to connect our Srad sensors to our flight computer, we want to have a multiplexer. So that way we have a way of being able to kind of hot swap components. So we can say like, hey, I want to do one launch using strain gauges, but I don't want the strain gauges to be part of the flight computer permanently. But I do want the flight computer to be able to collect that data. And then I can go back and say, hey, on another launch, I don't want to use strain gauges whatsoever. I want to use exclusively thermocouplers. And maybe we can do something like that on the ground station. So that way we can say like, hey, for this case, we want to be able to measure, X, Y, and Z. But at another case, we know X, Y, and Z. We want to measure A, B, and C. And that way we can plug those in as well. And then it's just, changing around a few libraries.
And for the ground station, I had a question like weight. I think you said, I'm not sure if it would be fairly lightweight.
Yeah.
Sometimes multiple things, something to carry in your hand and then another thing possibly. I'm not sure if I'm getting confused.
I'm a little bit lost there at the end. Are you asking if there's like two devices or?
Correct. Yeah, that's what you talk about.
One device. So the ground station will be one device for our build system here. As for the weight, we don't have all the components in yet, so we can't give you, an accurate weight. But within mind, looking kind of online at those weights compared to the weight of my laptop, which I didn't write down the weights exactly, but we're looking at somewhere that is like currently about 3/4 the weight of my laptop. And keep in mind that's with the antenna and everything. We'd also have to carry an antenna and a dongle and all these other things with us. And the actual box is something that I've just kind of selected from lab right now. They have some like spare cases there. It's a full metal case. We're going to switch it from something a lot lighter, but I'm using that just for dimensions. We can say like, hey, it should be this big, no bigger. And that way we have kind of a starting point. But ultimately, when we switch out that metal for plastic, it should go down in weight. And then as we start to kind of upgrade things and get better parts, because right now we don't want to request a lot of money that we don't have. So we're starting with what we have, and then hopefully we can move on to smaller, slimmer parts, maybe even SMD, and start building our own PCBs, and from there get like a lot slimmer in design.
The ground station, the one I'm referring to, when I think about that, I think about like a ground station that doesn't move, like it's grounded in a certain place, like I saw at that competition thing. I'm not sure if whenever y'all went tracking for for Oberon, if y'all took your laptop with you.
So for Oberon, originally that was the goal. Brandy actually gave us a little device right before we went to launch. It's a tele-BT, so we're able to connect it to my phone afterwards instead of using the laptop. But that was something that we kind of just got lucky with. It's like a $300 device that we did not have budget for, that Brandy just generously donated towards us. But ultimately, if we didn't have that, that would be exactly what we had to do. We'd take our laptop and walk out in the field with it and everything. And even then, trying to read numbers off of your phone is not always the most convenient, again. So a way to kind of optimize all of that and put it into something that's nice and easy to read, nice and easy to carry. And it's not feasible to have the entire time connected to my phone over Bluetooth. Like when Oberon's actually launching, we do have to use my laptop first, and then post launch, we're able to connect it to my phone to get the GPS coordinates and stuff like that off of it. So this would take place of both the laptop at the start as well as my phone afterwards, putting it into one device.
Yeah, based on that, so you want it to be mobile in a way to actually drop it. That's the first time I actually heard about that, because when we retrieved Oberon in Mexico, it was just then sitting in base, getting there, getting photos, and just walking that direction. So is there such a need that you have to have that connection while retrieving the whole time?
I would say it's ideal to, because we do have that antenna built into it. So in the case that we, for example, the rocket goes further than we expected and we lost connection towards it farther away than we would like to, coming near the rocket would mean that we may not be able to visually see it, but having the antenna with us means that we can kind of play a game of hot and cold, and based off the RSSI connection, know which way the rocket is and actually find it from there a lot easier. It'll spare a lot of time.
Okay. With that slide there, are you planning on having 6 different LEDs, or is it just going to be one RGB LED that can change colors?
We're thinking of 6 individual LEDs. The problem with the RGB LEDs is that they will take different voltages to determine different things. And if that makes sense, different voltages will change the colors. And we don't want to have, some kind of a misfire, maybe we overpowered something and then we're getting like a wrong reading and then we're wondering, like why we have this. So having 6 LEDs allows it easier for debugging purposes to just kind of denote that, hey, this is specifically wired to here, this is specifically getting the voltage that it needs to. And if it's getting over voltage, then we know that, hey, that's a different problem. That's not, our programming wrong.
I remember just on a couple of, you guys made a decision matrix for the optional feature.
Yes.
You guys weren't comparing it to each other, so the decision matrix wasn't really working.
Yeah, the decision matrix it wasn't like a standard decision matrix. It was more of an idea of, should we do these things or not? It wasn't like a, comparative. It was kind of a, should we implement these? It was just kind of a way to quantify for future years. If people look back and be like, okay, well, did they, think about if this was worth it? They can look back and say like, okay, they did consider it was worth it.
And the last thing for me is, well, you went quite a bit on about brightness, how difficult it is, and like trying to do all these different screens.
Just 2.
2 different screens, but then OLED, which is why don't you just make a shader?
Shaders do not always work perfectly. If, for example, if I have a shader facing this way and the sun is behind me now, it's still going to be, I understand, but even then, viewing through the shader is not the most, viewing through the shader is not always the most convenient, and it's still not always the most easy. Like I know sometimes, standing out in the sun, you're kind of like this on your phone, trying to read, And even then, when blocking the sunlight, it makes it possible to read it, but it's just not convenient. Versus an OLED, you don't have to do any of that. You can just pull it out directly, in full sunlight. You can read it very clearly, like you're reading a book. And yeah, battery consumption is very low for OLED. It actually is less than an LCD. And considering the size of the screen is very small, it's like, I don't have too good of a frame of reference for you, but think of it like maybe 2 inches at most across. It's literally just the size of the eye opens on a Raspberry Pi. So it's not too big, it's not too powerful. It's literally just enough to show altitude information or GPS location.
For avionics, I'm assuming the TC has, how you good at that, going to data log things on what's happening in avionics?
Yeah, so
Kind of storage memory.
yeah, so the TNT has non-volatile memory that we can write directly onto, as well as we have extra flash chips that we can add onto there, which is volatile memory, and we want to add in an SD card and hop through that in place. So that way we have complete backup.
Something that I learned that how are you going to be connecting our components? And for answer that, I think it's very useful knowledge to learn how to work with connectors, like connectors you could buy off of. You can think about like more transistor software.
So you're talking about like hot swap components?
No. Like if you have, let's say you have you want to connect your like this barometer to your TT, right? Instead of having like 4 wires to connect them, like 4 wires, you should have
A connection type for it, yes.
That you connectorize the barometer, and you connectorize the TC.
So
A little satisfying click, along with learning pinouts, making schematics. Because all the 4 wires will work just fine. But the harness is very important whenever you're cable management. I'm sure you deal with, you sure you know it's a pain in the ass that is not managed well. And as you get more and more complex SRAD things, they're just looking nice, especially the judges.
yeah, so a little bit on that, we do want to move to a PCB. In the bill of materials, we do have set aside $150 for PCB design because it will be kind of a couple revisions, obviously. So once we move to a PCB, a lot of those will be anything internally. So flight computer, connecting those barometers and accelerometers are going to be directly connected there. We do want to attach a multiplexer to it as well, and again, they'll be directly to the PCB. But the multiplexer outputs, I was thinking of using general IO pins. So that is something that we could make connector types on. So that way we have, a multiplexer. It has the IO pins coming out as like a separate cable. You kind of put that cable wherever you need to orientate it, inside of your rocket. And then you can plug into there based off I2C and ISP connections, which also answers the question of what kind of connections, if you were asking about protocols.
And what is the testing look like for avionics? Is it test flights? Is it vacuum chamber stuff?
A little bit of everything. So we do have a hobby rocket stream under AIAA right now. So we want to be able to put our flight computer into the hobby rocket stream computer, rockets. So that way we can kind of start testing around and see like, okay, we need quantitative real world data. Here's how we can get quantitative real world data. As far as on the ground goes, we do want to do pressure testing as well as kind of in a car to test acceleration and things like that. Just kind of drive around and see how the acceleration reads. And as far as gyroscopic data, obviously, just like, whee, device goes spin.
When you guys pattern, I know SRAD is sort of backwards and these along with but is this within this next semester?
We expect to be doing kind of some background work with it throughout the semester, and ideally, kind of have everything has a different deadline as far as the 4 parts go. Hopefully, telemetry can kind of finish up towards the end of the semester. At least have something. We're trying to get working telemetry working right now. We had issues with drivers, so we bought some knockoff drivers, not by like SparkFun or anything like that, and they didn't work. So we're trying to get something SparkFun drivers, and hopefully And funding will play obviously a big part in this because there's quite a bit of components that need funding. But assuming, you know, we get funding, for example, for the spec fund drivers, then we're able to immediately go into starting working with the team with the telemetry and start already talking about optimization and things like that. Ground station is kind of good to go. We're actually working on testing right now in a car and whatnot. Or sorry, not ground station. I'm so sorry, flight computer. We're kind of just working on testing all those sensors and making sure everything is running there. And then we're going to hook up the multiplexer. SRAD sensors, we're hoping to, towards the end of the year, get that one finished and, you know, potentially put it on Zenith if it's not too far of a stretch. It's like not, okay. Yeah, so it looks like not then. And then for ground station, that's probably going to be like beyond the scope of this year. We'll probably start on it, but definitely not finish it this year.
So, Zenith,
Yeah,
I also should know, but to be able to get testing, I think it's important you define a max level space volume requirement for the entire system and all of the weight. It's like if I'm designing a rocket small for myself, I need to know how much space, how much weight I need to reserve in my personal rocket while designing it in my open rocket versus open, you know, how big it is and how much is the weight. I know you don't have that yet, but just in the future, whenever you do define more things, is it a, you know, is it gonna be a 3 by 3 by 2 thing? Is it a weigh 6 ounces? You know,
we're trying to get those trait size in so we can finalize which devices we're going to be using, and then we can get this information.
Or even more engineering challenge, we define that now. So that's why that's what happens a lot of work. Someone tells you, oh, you got this to work.
Yeah, that's valid.
Make it work versus, you know, you have infinite space and weight. It turns out no one can do every honest thing up to this 1,000.
Yeah, we're definitely trying to optimize this as much as possible.
Also, right, you guys have custom PCBs that's on your budget?
Yeah, we have $150 listed on there to kind of be able to do PCB design.
And is that for flight computer or for everything?
It's going to be mainly for flight computer. I mean, obviously, we're going to have probably more money going forward for like ground station and things like that. But flight computer will encompass telemetry as well as SRAD sensors. And then ground station will obviously accompany telemetry as well. So
That will constrain the design or size wise.
yeah.
And last thing for avionics, see thermocouples in there, some stuff, maybe else I thought about earlier, but I can't think about now. But I think you should try to talk to the engineering lab professors. I know, for example, Dr. Love, the one of those thermal fluids along with thermal, she runs the fluids lab, and she has like a spool, actual spool of thermocouple wire. And she's been sitting there for like I don't know how many years. And she only needs like 3 a semester or whatever, or 10 a semester. And all of them may not be expensive. That's something they possibly ask for.
Get her information my way, that'd be amazing.
Coming up a couple slices of that, and that's like, you know, but and that's the thing that yeah, and so like
I feel like, can I get 100 feet of this?
you're not mechanical, right?
No, I'm not mechanical. I'm computer science.
I'm mechanical, so I will know that just because I deal with Dr. Love. But you know, I'm sure plenty of people here mechanical, they want to be in contact with Dr. Love, for example. But even I'm sure you have plenty of professors in electronics realm that deal with other things you may need, but you can reach out and say, hey, do you have whatever the hell, whatever you need, I'm going to read you that right now. No, I know what the hell that means. I'll have a lot of stuff there, but just a thought.
If you have any questions about this, feel free to message me. So if you have any questions about what any of the stuff there means, feel free to message me.
Don't you already have an XLO JavaScript from the
I think we do. Yes. Is that?
Do we have a cost for it? Where is it? It might have been an accident.
On the right side.
On the right side. Which accelerometer is it? Yeah, we actually have this exact one. Yeah, I think that was an accident. Yeah, we do own this one. Yeah.
Yeah. $800,
That's my
wow.
contribution. That's my contribution.
From 800 to 11 to $800, perfect, so on the money. Oh, yes, my name is V.
Yeah.
My bad.
I just thought that's all I have for avionics. So I came in late, sorry about that. I would like to catch up. When are you all trying to launch by again?
For SRAD? Oh, man, I'd say, for what?
For prop in particular, right? Yeah.
For SRAD propulsion?
Yeah.
Yeah, probably not. I mean, we haven't even begun testing the injection system. This December, that's gonna happen. I'd say we won't even be able to run a full engine test until 2023, and that's like
Wow.
next year, and that's
What's keeping y'all from?
mostly just funding. That's the biggest thing, because we started this as soon as we started developing Zenith. All that, funding goes into Zenith. Now, if we somehow got like $15,000-$20,000 of funding all of a sudden, and they're like, hey, Ozzy, here's $2,000, do what your team needs to do. It's like, yeah, I'll probably get a couple of prototypes working for, but that's how it is. And then for flight, I mean, a good estimate, even a year after that.
I guess just more on that. Yeah, so all this address stuff is long-term, and it's really gonna depend on whoever the project manager, chief engineer is next year, whether or not they're gonna continue to do like a Zenith, like another COTS rocket, or if we're just gonna put all the efforts onto a hybrid rocket. Yes, yes, no, yes. Since AIAA is our parent org, we work with them to reach out with companies and try to get funding from them.
So the reason I'm asking is, right now, there's a huge push for Houston to become big in space again. A lot of companies in the space board are pushing to fund the city back from that. Two missions down there, Ashland down there. There's where the Virgin Galactic is moving down there. The city government is also putting a lot of money. And I mean, I don't know how feasible it is, but I'm thinking of it's Austin that got fired by sponsorship and they don't want money granted, but they're becoming a powerhouse. I don't know if y'all could maybe try to convince some magic, try to talk to some of these companies, maybe to the machines are getting a lot of funding, some Axiom. It's worth asking, and you'll have to know. But you can tell them, hey, we have a lot of students that could potentially be a pipeline to your company in the future. If you mentor us, we give us money, we can make on a rock or something. You can benefit from that very, very, very as well.
Yeah. I think another thing to that is the entire hybrid engine hasn't been modeled up at all. So it's just, the capsule team's just been focusing on the injection system. So I think that's actually one of the first things that I want to tackle is to work on the pressure vessels, and as well as having like an exact model of what we think the entire hybrid motor is going to look like, and then work off of that. And I feel like once we have that, then we can present, hey, now we have a hybrid motor engine rocket engine that we can then show other companies like, this is our model, this is what we're working on, this is what we want to do. And I feel like it'd be a little easier to get SRAD funding if we had that information, or that next, what's it called? Project overview, basically.
For sure, and modeling is not expensive. You need to buy things to do that. So I guess what's a timeline for you to have that?
Honestly, that's probably one of the first things I'm going to start working on next semester. So come January, February, go into a lot of 3D modeling. I know the test stand 3D modeling, the modified one, it's been going very smoothly, very quickly. I think I'm confident that with a couple of SRAD propulsion members and even some analysis members who've been doing a lot of 3D modeling, we can get a good model in 3 months. Of course, it's not going to be exact to a finished product. It's just going to be a lot of estimate and theorizing, but we can get a good enough looking model for the for the newspaper.
I do want to add to that. What you said, and something what Abraham mentioned is I think I'll talk about that. I remember, but showing companies that you broke is great. And the reason being is if you have model to do still, then it comes up with late like, listen, man, this is free from my school, like the printing lab. I'm like, we're too broke to even get something. So like, obviously we want to do this, but like, versus like, we don't have a model. I'm like, okay, well, why did it give you 200K? Like, why?
Yeah.
So like using, I'm sure, I know the AIAA, Rocket has a 3D printer in house, right? And then U of H, at least any department has a 3D printing lab to send crap to AIAA for development. But just like having a full model of an engine or motor to show for the competition.
Yep.
To appeal to other companies. Probably a good idea.
Yeah, absolutely.
Imagine going to the training lab and be like, it just.
You still taking off some sections and group together. It's not gonna be functional, right? Just like,
Yeah.
if you want to eat a tank this big, you want to put up to 8 sections and super glue it together. And it's not gonna hold any pressure that you want to shove these.
Yeah.
We
We'll
want to
see CR10S at the lab. I think we'll be fine.
Yeah, not gonna afford super glue and afford a composite or pressure vessel.
Yeah.
I don't know, super glue might be out of budget.
So why are you currently machining the injector?
So that was actually done through one of the manufacturing organizations that works with Capstone. I don't exactly know who they mentioned, but that was done by the Capstone team. So they provided the materials and were provided with the resources to manufacture that. So for me, it was literally just one day they had a aluminum rod, and the next day, like, hey, they made it. But I think it's an important thing to consider, especially whenever we start making pressure vessels, to actually get a good organization or manufacturer for that. And I think we already have a couple sponsors who will help us with that. But I know whenever I was talking to one of the guys from the Rice team, they also mentioned to work together to create some of those, because they have a lot more machines, they have a lot bigger lab, and they've actually already had several hybrid motor tests. So we were going back and forth and just talked about, helping each other out to complete this project.
So was the design made in-house?
Yes, that was actually made and what's it called? The fluid analysis, what is it called? CFD. So they actually did do a lot of that testing on their own, and then they made and machined it.
Are you always using answers or
What was that?
answers or what are you using for CFD?
I believe, man, I can't think of it. I'd have to ask them and get back to you.
And then another question, how, I see that you tested the injector, right? Or water flooded.
Yes, yeah.
How did it perform compared to your operations?
So of course, the injector was tested without a gasket first. Obviously it leaked, but they did, I gave them the idea of using just a cork gasket, something inexpensive. It was like $8 at AutoZone. And the way we made it is we literally just put a piece on it, cut it with an X-Acto knife, put it on there, and it actually held up significant pressure. I mean, up to 2 times the amount of operating pressure needed. No leaks. I mean, the injector's running perfectly fine. So that was with water, pressurized water. So what is it called? Pressure washer. Jeez. Yeah, it was with a pressure washer. That was a preliminary test, but they did purchase a CO2 tank, which they want to test with it, something closer to what nitrous would be like. Yeah.
Was the amount of water that fell in the bucket, the amount of weight of water you still expected for the flow?
I wasn't there for that test, actually. I was just, they did show me all of what they did. But I assume so. I assume some, they haven't told me otherwise, and they're still going forward with the project. So, and of course, we're probably going to test that even after the Capstone team's done.
I don't know, I guess, you mentioned money, that's obviously a big issue, big setback, but what are some other technical issues or setbacks that you're facing?
So most of the technical stuff has to do with the fact that this is our first time doing a hybrid motor. or engine, I keep saying motor, but engine, you guys get it. Some of the setbacks could be, for example, like structural setbacks. I know they have come up with an idea of how they want to do the bulkheads and also what materials they wanted to use. But of course, they had to take that out of their scope of work because they couldn't meet the timeline. So now that falls on us to actually do the analysis, do the CFDs for different pressure vessels. And of course, creating the combustion chamber, connecting that to the oxidizer, because the entire motor has to be like a solid piece, right? You can't have any slack between them, else, that's bad. So most of the setbacks will literally just be starting off. I mean, it's a brand new project. And honestly, the thing that I'm most concerned about is the pressure. I mean, that's the most dangerous part, really, up until you start testing actual fuel. But that's my biggest concern is just the pressure vessels. It's going to be a lot of research, a lot of testing before we even start manufacturing. And I'd like to start off small,
Yeah, I mean, I have small, very specific questions we can talk about.
Sure, of course.
What are your goals for the end of the semester?
What are the what?
The goals.
The goals. So the goals for the end of the next semester is have that 3D model. So I want to have an idea, because we've had the injector plate model up until now. And of course the valve control and that stuff. But currently we're using like this epoxy resin combustion chamber just so that we can have a clear view of the injection flow. And that is actually curing as of speak. So hopefully by Monday, I'll send you guys some pictures of how that turns out and how it bolts to the injection point. I didn't put anything on here because it's literally just a PVC tube. With the epoxy, you just gotta believe me, there's epoxy in there. But by the end of next semester, I'm hoping we can actually have a fully rendered model in an airframe with the mounting mechanism, developed or modeled up, just have like a really, really nice 3D model that we can present to, projects and work off of that.
I would say shorten that timeline on
For what?
3D modeling should not take you.
No, absolutely not.
And it can be done by the end of this grade. You should be able to go into the new semester with at least the first version of the model. And
Yeah.
throughout the semester, make minor tweaks and this needs to be an inch longer or shorter or like that.
Yeah.
Instead of giving you 2 months to do it, give yourself a week just to have something.
Yeah, of course.
And just slowly add to it.
Yeah. I mean, we also do have a lot of other projects to work on, so it's not like we're going to be modeling the entire time, but yeah, we do have a couple other stuff to work on, specifically with solid fuel stuff and chemistry department stuff.
I want to ask about that. Why ammonium chloride? Why not sugar?
So main reason, we did find this, and we were working with propulsion, Cost Propulsion and Irvin last semester. We did do a trade study on different fuels. And the reason we chose ammonium perchlorate specifically, it was a cherry limeade, one that was produced by MIT. We want to tackle that one because it's a fairly new, still very well tested mixture. But it also gives us an idea of like high powered rockets. I know that sugar motors aren't as powerful, like the fuel itself is not as powerful as the ammonium perchlorate composite. So it'll give us an idea of the current fuels that are being used in some of the motors like Loki or the Cicerone motors. It's almost identical, minus a couple different changes for visual effect. And if we start testing that small, like if we start doing minor testing, it'll give us like a real life representation of what the bigger motors are going to look like.
I mentioned that because what would that cost look like? Cost difference.
So the cost is, yeah, there's
I made a sugar motor and I went to HEB and I went Home Depot. I made a motor.
Yeah, exactly.
And
So
I mean, it's like,
no, you're perfectly right. So we do have some of the composition by weight percentages is also, as well as like batch calculations for the fuel mixture. Up on the bill of materials is just some of the biggest contributors to the price. The main contributor to the price being I think it was like 200 micron or something, ammonium perchlorate, 200 or 400, one of those two. That is the biggest cost. However, that is for, those prices you see there is for a full Loki M3000 reload. So that, I mean, we're not going to start off making 9 pounds of propellant. We're going to start off making like half a pound and testing a little motor. But I put in the price for a single reload just to give us an idea, comparing the cost of mixing our own fuel in-house compared to actually buying a reload online.
I would, I recommend you revisit the sugar thing.
Of course.
When you buy, when you buy a pound, buy a kilogram, buy 5 pounds. You can't buy a half pound more unless you're going to crazy box store I've never heard of. That have like really weird, like, you know,
Tiny Ziploc baggies of
type situation.
self-serve.
Yeah. Now that exists, if not, let me know.
Please, we'll make one.
But again, you can buy 5 pounds of sugar for $1.50.
Yeah, that actually,
Stuff for $5.
that actually sounds like a good idea.
So, and you can talk really, really small. Also, how much equivalent of explosives is this for an overpressure event, aka blowing up? And how far you have to be for something as high energy as a morning prefer, which is obviously a clearly high power rocket.
Yeah.
High power rocket and motor versus sugar, which you can make pretty big, but still not be high power.
Yeah.
And along with testing, like locally, and like if you would have a overpressure event,
Yeah.
well, what would be your maximum or minimum safety range? You cannot do that anywhere on campus. Like
No.
you do that elsewhere.
Yeah,
So if you don't have a 300-acre field to test this high power thing, you may want to start with smaller. So the equivalent of like an M60 firecracker versus
yeah.
high power.
Yeah, actually, I have heard talks that they want to put a test stand at the south side. Is that correct?
They've been saying that, but they're also relying on us for providing the site, like providing the
Foundation.
the actual concrete pouring
Yeah.
and rebar and which I'm not qualified to do that.
I guess just on that, we ended up last year, one of the things we had in plan was helping them provide the foundation. And we actually got a civil engineer to help us out with that, just make simple calculations. And again, because of funding, we weren't able to do it. But we have some of the foundation already for the foundation.
Couple of YouTube videos and stuff. But yeah, so yeah, that is a good idea. It was never my intention to test like a full-sized M-class motor because the overpressure can be pretty dangerous. I mean, you can sit there and do nozzle geometries for like, calculations for like a week straight. You never know if it's going to be exactly optimized. It's one of those things you have to test over and over again to get a good optimization. And in an event of an overpressurized, I mean, these motors will run approximately like what, 1,000 to 1,500 PSI. That's operating pressure, combustion chamber pressure. I know the motor casing we have currently, that one's been rated for up to 3,500 or 3,000 PSI. So there's a good factor of safety there. But if we start manufacturing our own combustion chambers and mixing our own fuels, it can get pretty dangerous. So I think making sure that the combustion chamber is actually pressure tested without propellant, probably just getting like an air pressure or like water pressure, that kind of stuff. Pressure testing it without propellant, and also starting off small. That's really, really crucial. And as far as how far we got to step back, I mean, as far as we need to, really, we can definitely make some calculations on the like how it bursts and velocity and stuff like that.
Your calculation for like, I think like for use for whenever they blow up like mines, like if equivalent how many tons of TNT or how many,
Yeah.
How far they stand away. There's calculation for that.
Yeah,
I'm
of
sure you
course.
can find it somewhere online. I don't know that.
Sketchy sides and stuff.
Something else. Why? I was talking earlier about it. Why make the modified test stand stronger? I know that was something that talked about some point. My understanding of making it stronger was not liking the friction fit fittings that it has on there. I believe that was the issue. Those friction fit fitties can withstand the amount of load, whatever motor class you want to do on there. There's no need to change that, because of the factor of safety. And the way of testing it, I think of like bolting down what you expect to bolt it down to, and putting like a car jack underneath it, and like doing it to the amount of thrust you expect to, and it doesn't move it.
Yeah.
Yeah, all obviously with the factor of safety is 1.5 or 2.
Yep.
So versus spending your time and money on modifying it to which one.
So that is one thing, is I didn't want to spend any money on it. So we did not spend any money on it. We actually found a couple bolts laying around and in the lab, like a lot of them. And we went off of that measurement for the bolt, and it actually ended up fitting perfectly. The entire test stand was basically flipped upside down. The test stand was mounted before so that the thrust was pointing up, exhaust down. So the first thing we did is just flip it. So now the main base is at the bottom. Motor mounts onto the base, onto this 3x3 inch load, what's called beam that holds the load cell. I was trying to do analysis on the beam, but apparently my computer doesn't have enough memory, so for that analysis, but it's fine. The next thing we did is we literally just started drilling and tapping holes, and every single one of the arms, frame rails, everything is just bolted together using some brackets, using some like inch long bolts. I mean, the only cost that I see that test stand inquiring would be like the cost of 85 1-inch 5/16 bolts. That's the biggest cost. And then also how to hold the motor down. So just like make a mechanism or some arms that will actually hold the motor onto the frame straight. So luckily we haven't spent a single dime on the test stand, but we did modify it. And it is actually a lot stronger already because of those bolts and connections. But yeah, I think it'd be awesome to test it. I mean, we've done some minor testing, like pushing yourself on each beam and stuff, but something like quantitative that we can write down. Yeah, take it to the gym, basically. Yeah.
Do you even live, bro?
Yeah, I forget who it was. I think it was like Adam Savage. It's like the only difference between science and messing around is who writes it down. So,
some other stuff. How are you turning the valve? I know there's a big push. Maybe get talk about it more, but how cryogenics or cold stuff and valves being terrible.
yeah. So the valve you see there was actually not the valve they went with. The valve you see there was just like a minor valve just to test the pressure washer. The valve they have now, I don't know the exact specs for it, but it's like a much more robust valve. The valve itself, they made sure to be tested with cryogenic like properties, I guess.
I want to repeat my question.
Go ahead.
What do you turn the valve?
Oh, so there is a low speed, high torque electric motor that they're using with a gear reduction. So a lot of different project teams use like a chain drive or something to actually spin the gear. But they opted for a injection molded gears that will provide the gear reduction for the valve itself. So that's the way they're doing it. And they're hopefully finishing it up pretty soon. I have been with them while like assembling and test fitting all of the gears and stuff. And it looks robust enough. Maybe changing that to a little bit stronger materials down the line. But as far as for the testing goes, I think it's enough for the testing. But that's how that works. The motorized drive, the motor will be connected to the microcontroller itself. So it'll be wirelessly, or not wirelessly, but controlled by Teensy.
So it's okay to use the gear reduction with the slow turning of the throttle instead of like a quick jerk the whole one of the throttle type stuff.
Yes, it should be enough. I believe they did like a minimum flow rate and maximum flow rate that they wanted. And even like a slow turning valve would give them that minimum flow rate that they were looking for.
Those are the questions. Thank you.
Cool.
I have two of the questions. Don't need to answer or anything, just something for you to know. How are you measuring fuel regression in the hybrid motor? I have no idea how to do that. I'm sure there's a complex group of papers out there about it. right on my head. I have no idea. Along with a suggestion, if you guys want to make composite over pressure wrap vessels around the LCOPs, I recommend you reaching out to any of the manufacturers and asking for a tour.
Yeah.
You know, I know there's epoxies and things kind of expiration date, and why can't they go to trash? That'd be pretty cool if they have like laid things of carbon fiber, like can't make anything with this, so why not give it to this college team that's like starving? So I mean, like reaching out, it could be some in Houston, I have no idea, but you should look into that. Not only for asking for money, just ask for a tour, because you want to get into that.
And then be like, hey, you have that stuff laying around over there.
Possibly. But just asking for a tour, just maybe they can show you some cool things that they're doing.
Yeah.
And maybe they can be excited.
I think those, yeah, I think those carbon fiber, like composite pressure vessels, I think we're going to start off with like regular, like aluminum or stainless steel ones. But that is ultimately the goal, is to have like a carbon fiber wrapped pressure vessel. That'd be pretty cool. I mean, that was the goal from the beginning, but you know, much. It would be really cool if we were able to make it in-house, but I don't think we have the right tooling for that yet.
You can also just like the small pressure tank on top of the hybrid top box layer. You can just use a paintball.
Yeah.
Same thing, super light, or like 8,000, 12,000 size.
Yeah.
You can buy it off of Amazon for like 100 bucks.
Yeah. No, I.
Probably more than enough. And it's super cheap.
Yeah.
And it's not.
Yeah, I actually have been paintballing. I think the tanks are a little cheaper. Like
I mean, for the.
But yeah, you're right. You're right.
Some are the COPVs I'm talking about, but like weight cost like this.
Yeah.
12,000 PSI somehow.
Oh, you talk about, yeah, okay, yeah, that's pretty
Yeah,
tense.
but anyway, that is another note.
Yeah, of course.
No other questions.
So about the strength gauges, I understand they won't be on Zenith, so it's a goal to have them on rockets in the future. Yeah.
So I'll take like the first part of the question and then you can continue. Yeah, so I guess the decision we've made this year as far as Zenith goes is to anything that's not like required, like the sensors or everything analysis did in previous years is not going to be on Zenith. So that's when V and us have other plans for that. I know hobby rocketry will be a huge part.
Yeah, so ideally we would be able to test it in hobby rocketry and, you know, any other rockets that people might be launching, just to give us kind of real world quantitative data to make sure that what we're doing is functionally correct. And that's why we're still, you know, we're still doing these trade studies and we're still trying to get our strain gauges in, you know, as soon as possible. But yeah, ultimately they're probably gonna have to be done on hobby rockets, probably through hobby rocketry, to get quantifiable data first, you know, make sure that we have everything up and running. And then in future years, we can add it onto our big rockets.
Okay. That being said, is there how many bits do you take?
3 to 4. So for an L1, I would say 3 to 4. For everything beyond that, it's normally around 4 fins. So you can expect about 4 fins.
Okay, I was thinking of like, I saw in the bill of materials there were 4 strain gauges.
Yes.
So I'm thinking, pending, because the strain gauges have to be able to bend the fins.
Mhm.
So I'm thinking about the ability to reattach those strain gauges because they have to secure bend with the fin.
Mhm.
And
Have to be able to remove and place back.
yeah.
So I will say that with our experience with the strain gauges we bought off Amazon, which are not our, you know, perfect representation or anything, those are very bad strain gauges. But, you know, with our experience with those, they were fairly easy to move and remove. They were able to kind of tack to their surfaces just fine, and then remove and then retack to other surfaces. So ideally, that's what, you know, whatever the method they use for those strain gauges will be something similar for these strain gauges. I think that was the only thing those strain gauges really did good, which is why we're looking at new strain gauges this year. That's something that I'm not expecting it's going to be enough heat on there to cause any issues. But that's something that we'd have to test because, we can, take our guesses, we can, do this and that, but ultimately the environment conditions will probably matter the most. If we come to New Mexico, and we launch it in 104-degree weather and it adds on, let's say every flight, argument's sake, every flight adds 3 degrees and, it operates under 105 degrees max load and we come to in Fahrenheit. And we come to New Mexico, it's 104 degrees, then yes, it's not going to work. But if we launch here in Houston and it's 90 degrees, then we're just fine. So a lot of that will be environmental, and we can account for it as much as we can, but there are some edge cases there that we just can't deal with. So we have to go under the assumption that it will work. And obviously something that we do want to look into as we're doing that, make sure that it has it's not going to stop working at 70 degrees Fahrenheit or something like that. But otherwise, yeah, it's something that we just have to hope that it will work over, a little bit over 100 degrees, because that's probably what we'll see in New Mexico. Yeah, ideally, we can start also quantifying some of that data with Hobby as well. So we can see hey, if a Hobby rocketry, if in Hobby it gets too hot from the force of, just the drag force on the rocket, if it gets too hot there in Hobby, then we know obviously it's not going to work for a competition rocket. We have to do something else. So it also kind of give us a little bit of information there, not, the most, but something to at least have some more of a premise of. Any other questions?
And I've sort of been I like the models, and so I've been sort of learning and probably have one.
All right. I think this is it for today. Again, I want to thank everyone. I want to thank especially everyone, alumni. I didn't get your name. Abraham, Eric, Dom, and everyone else. I know Michael was online. I thank y'all for all the feedback and the questions. This is very exciting. We hope we can get the funding, get the work done in one day. Hopefully soon see some results. But thank you to the leads too and our moderators. Thank you. Taking notes. Any questions? I can just probably type it here, but any other questions or anything, I will write down my email here. And then Gustavo will also write his email. I wrote this. You can just email us or ask for a phone number, and then we can get in contact for more advice. Thank you.
Don't come today.